So we finish up Chapter 13 of Young and Friedman's University Physics with a section on what are called forced oscillations and resonance. This is the 8th section of this chapter. The math in this section is again a little bit advanced. They don't even do the math. They could just kind of tell you what the equation is. It requires a little bit of differential equations, which is like 4th semester calculus. But basically, a driving force is a force that is in addition to a natural oscillation. So let's say you have a spring going, normally. A driving force is an addition, something outside the system. The best thing to think about, I think, is a swing. A swing, you're going back and forth in a swing. That's a kind of a natural angular frequency, back and forth, back and forth. Most of us have pushed someone in a swing, or if we've been in a swing ourselves, we know that we just kind of learn how to move our feet at just the right time to increase our amplitude as we're swinging. Or if you're pushing, someone in a swing, you know that there's just that sweet spot where you push them at just the right time and you get a maximum amplitude. Those are all external forces, driving forces that can keep an oscillation going despite damping forces, or it can amplify the amplitude as well, even when there's a low damping force. So I think one thing to remember is this idea of a driving force isn't just to overcome damping. It can increase even when there's little damping. Okay, so we call this forced oscillation or a driven oscillation, and it's basically what you discover is experimentally, and it turns out that the math works as well, that an oscillation is best maintained, or that sounds like it's just about overcoming damping, but the amplitude is going to be greatest. Let's put it that way. The amplitude is going to be greatest if the external driving frequency is about the same as the natural angular frequency. So that sweet spot when you're in a swing, moving your legs or pushing someone in a swing, when what we're experiencing as the sweet spot is where that our external force of our legs or of our hands is just about the same as the natural frequency of the back and forth in the swing. That's going to be the maximum amplitude. And we call that resonance. That sweet spot is called resonance. You've experienced resonance probably at some point. So as I've mentioned, pushing a swing just right, or moving your legs in a swing just right, so that the driving force and the natural frequency, are they're in sync, and so it's just right. You've all heard about the attempt to break glass with your voice. That's again, it's about resonance. It's about the driving force and the natural frequency jiving together. Sometimes you may have a car that at a certain speed, just the right speed, it rattles. That's resonance, where again the force has hit that sweet spot of the natural angular frequency. Sometimes you'll get a buzz in a speaker at a particular frequency. Very annoying. Tuning a radio receiver. What is it that brings the station right into clarity? It's because you've hit a resonating frequency with the station. There's a story, I don't know when it happened, but apparently when you're marching over a bridge, it is normal practice to break step because at some point in the past, I don't know when, at some point in the past, soldiers marching over a bridge, left, right, left, right, left, right. At some point in the past, the soldiers were so in resonance with the bridge that it actually broke the bridge. And of course, if you do a YouTube search for the Tacoma Narrows Bridge, Galloping Gertie, you'll see a bridge in Washington State that it's still debated exactly what, and Young and Friedman give another alternative, but it may have come down because the frequency of the wind just was right with the bridge, and it just amplified until it hit a resonating breakup, as it were. So resonance is something we experience, and it has to do with when the external driving frequency is at the same basically coincides with the natural angular frequency of whatever. Now here's the formula. The amplitude of a driven oscillator. Here it is. Now they don't tell you how they got this formula because it involves differential equations, and I've seen other versions of this formula. This one is actually fairly simple compared to some other versions of the formula I've seen. But basically, if you and a lot of times, for example, it's easiest to understand this if you think of this maximum force in terms of a particular kind of sinusoidal function. So you might see, him mention something about cosine of omega t plus phi. That we're formulating the force in terms of a cosine function. Again, you don't have to understand that, I don't think, to get through a first semester or second semester physics course. But here's a formula for the amplitude, where you should recognize most of the terms here. F max is the external force that we're applying. K is the constant of the oscillator, spring constant or whatever. M is the mass. Omega d is the driving force, that is this or the driving frequency that we're applying to it. B is the damping constant. Okay, so those are all the players that we've seen in the previous video and this one. So the maximum is going to be where this term becomes 0. That's going to be the maximum amplitude when this term becomes 0. So when k minus m omega d squared equals 0, you can see that if we solve for omega d, that's when omega d equals the square root of k over m. Well, what is that? Well, the square root of k over m is the natural frequency, the kind of natural frequency from a simple harmonic motion. And so when the driving angular frequency, omega d, is equal to the natural frequency, that's when we have a maximum amplitude. Similarly, the lower the b, the higher the a. The lower the damping constant, the higher the amplitude is going to be. They're inversely proportional. And then lastly, when the driving angular frequency is 0, then the amplitude is just going to increase directly as the force increases. Okay, I think probably when you get to an advanced physics course, you will go into a lot more detail. In fact, if you take a differential equations course, this is going to be, basically the case study, I think, for certain kinds of differential equations. So a lot of stuff here is a foretaste of what advanced physics or advanced math might be, but this is probably enough to get you through a first or second semester calculus course.